and we go even deeper into electronics manufacturing. Our next presenter is Bob Willis, who has been running a successful training and consultancy company for many years, with a wide range of training topics and training resources in the industry. With his online and hands-on training topics, he supports engineers worldwide. And I think the question is, how can production efficiency be increased in an extreme way? How can the manufacturers significantly reduce costs? How to prevent damages to components and PCBs? Bob shows us that that in the ongoing industrial revolution, the low temperature assembly and robotic soldering are also critical parts of the new manufacturing technologies. So I think the floor is yours now. Bob, are you here with us?
Yes, I'm here,
okay.
Willing and hopefully ready to go.
Yes, it's okay.
Yeah, my check slide shows that I'm ready to go. Okay, so basically, thank you very much. So let's get into the presentation. One of the things that obviously want to talk about is low temperature assembly and robotic soldering, and that's the topic that I've been asked to present. And I'm presenting this on behalf of SMTA Europe. So straight on to our subject of today. There is a lot of information on low temperature soldering out there in industry, and if you talk to suppliers and other vendors, you know, there is information available. 4 of the books I've shown here are available in the industry. They all cover low temperature, but more recently, a publication which was edited by Jasper Barth has a specific subject area or matter, a chapter directly relating to low temperature, based on a lot of the work that's been done by Intel on this particular subject. If you're interested in the books, I don't sell books. I just review them for many magazines worldwide, and I just thought that was useful as a piece of background information. In addition, as part of this webinar, I've got a set of wall charts which cover manual assembly and soldering with low temperature. Again, they're useful as a training aid. They're free of charge. If that's something that may help your staff in the future, then again, just drop me an email. So let's get on to the subject. Now, low temperature is not new. It's been used for many years, but it just depends how low you actually want to go during the soldering process. So if we look at some of the aspects, well, reducing temperature during reflow, hand soldering and selective has benefits to the environment, but it also has benefits to the longevity of the equipment. And it also overcomes some of the issues that we've experienced over the years, which is damage and warpage of components. And as components become smaller and smaller and smaller, that minor warpage has much more of an impact on the assembly yield and assembly process. So much of the data that Matt was talking about can actually be generated by defects because of warpage of packages or PCBs. It can be used very effectively as a double-sided process, so double-sided surface mount, something that most engineers are familiar with. And a lot of engineers are aware of the use of through-hole soldering, what we call pin-in-paste, intrusive reflow, multi-spot soldering. So low temperature can be used and benefit those processes as well. Potentially, there's cost savings on materials. It's a lot more difficult to get cost savings on components because, generally speaking, most component manufacturers only build for one market. They don't build for consumer and high reliability. So the actual package is the same nowadays. But on substrates, base materials, solder finishes perhaps, you know, there is potentially cost savings to be gained by using lower temperatures. Lower temperature alloys, materials are available. They can be used, as I said, in intrusive, but also in wave and selective. And you'll see these actually being used purely as a reduction in cost and cost scrap, so less joss generation. One of the things that does cost a lot to overcome during manufacture. Most of the focus from some of the researchers has all been about lower energy consumption. And we'll talk about this a little bit later on. And of course, potentially faster process cycles because of the reduced height or high temperature we have to try and achieve in the processes we're trying to conduct. Potentially lower aging, because if you think about it, if you're using copper OSB, you're using tin, which I don't like as a surface finish, personal opinion, we're reducing the effect on that for second side reflow and then through hole soldering. So that's, again, potentially a benefit. However, you have to think of the activators used in the different soldering materials and whether they activate at the right temperature, because if we change one thing, something else needs to change in the process as well, or in the materials. I've already mentioned that if we have lower temperatures, we can have lower oxide and dross formation, and potentially at lower temperatures, could we possibly go away from the use of nitrogen in some processes? Not all, but possibly some. But obviously the focus to a lot of engineers has been improvements in processing and the reduction of board warpage and component warpage, because not all companies have the ability to measure the degree of warpage we have seen on packages in the industry. It does take a lot of effort and of course money to actually do that, particularly for small contract manufacturers. Now, one of the things highlighted over the years in terms of defects have been head in pillow and non-wet. Head in pillow, where the two surfaces of the solder don't actually come together and form a joint, or in the case of non-wet, where the paste is actually lifted from the surface of the board on solder spheres on very fine pitch packages. And of course, if there's no solder on the pad, we can't ever get a solder joint. And one of the reasons that has occurred over the years has been warpage of the package. As we illustrate in this simple video that I produced a couple of years back, you can see the solder paste reflowing on the pad. You can see the solder sphere just above that surface. So that's your lift that's been generated possibly by warpage of the board or component. And the end result is an open circuit, difficult to find, intermittent joint. But that's just one illustration of some of the things that possibly can be improved on with a move to other materials. Now, when we talk about other materials, we're talking about low temperature. And basically, there are a couple of different families. First of all, the tin indium material, which has been around quite a long time. And I've used this for rework of BGA packages successfully. However, the disadvantage of that is the cost of the raw material, the total raw material. We've got tin bismuth and we've got tin bismuth silver. Again, these materials have been around for quite a few years. They weren't really considered too much during the implementation in the US and Europe during lead-free, because the materials have been proved and been demonstrated to be more brittle than existing materials within the industry. That's one area we need to consider and think about. However, when we went to Japan in 2001 as part of the Smart Group initiative, we saw examples of tin zinc, tin bismuth being used on consumer and what I consider high reliability consumer electronic products. So they were being used, and there was great debate between both engineers and scientists at that time about the validity of using these materials. So there is experience out there. If I go back to 2002, I messed around with tin zinc materials when I returned from Japan on some products. But one of the problems with these materials is wettability on surfaces, high oxidation rates within the paste itself. And as you can see in these two video clips, the wettability onto certain surfaces can be delayed. So these materials also were very difficult to print because they had a very short life expectancy. They went from beautiful solder paste to something more like cement, and then a solid cement after literally a couple of hours. So they weren't the ideal solution. But again, that's us learning about materials. More recently, INEMI brought out a roadmap and said showed or illustrated the growth potentially in the use of low temperature materials. So again, it's something we need to be aware of, even though it may not be as valuable to you as an engineer at this moment in time. It might in the future. Now, the Intel group looked at the cost-saving advantages, and they looked at the running costs of reflow ovens within different plants, and were able to demonstrate quite obviously there was potentially a reduction in energy consumption, and of course with it an advantage to the environment, and plus an advantage on the cost of running factories. So that's one thing that is a clear, tangible thing that managers love to hear about, anything that saves money. Now, if we look at products, but products are getting thinner and thinner and thinner. And I illustrate here just one example of a laptop board. This is quite thin. It's less than 1 millimeter, probably around 0.6. It's quite flexible, but we're putting quite complex devices onto it. So we have to look at how we're going to handle materials to get the best yields in the manufacturing process. So let's step back for a second. When we talk about low temperature, originally, a lot of people use this technology for rework and repair of BGAs to reduce the possibility of damage to parts, adjacent parts on the board, and of course, reduce the warpage that can occur. So during the reflow soldering with either the tin indium or tin bismuth type paste, the material reflows, it wets the solder on the sack ball, just like with tin lead, when we reflow tin lead with sack balls. The ball does not become a liquid, but the material joins together to form the joint. And the amount of time, the temperature, the amount of reflow operations will have an impact on the combined area. So where the tin bismuth and the sack, in the case of BGA terminations, actually reaches. And that's something that needs to be borne in mind when you get more into the impact on reliability of this process. If we look at this simple example, if you're not quite understanding as I'm explaining, this is just a simple demonstration of low temperature soldering solder spheres on a BGA package. Well, they're not actually on a package, they're just little balls at the moment. But the point I'm trying to illustrate is we're making reliable interconnection with the pads to the solder spheres. And if I then come and push one of the spheres, you can see the sphere is not liquid. So we're soldering to the termination. We're not actually reflowing both terminations during the soldering process. But it's exactly the same as perhaps Matt in his earlier years soldering with tin lead technology to high temperature balls, high temperature columns. They form a reliable joint, but they don't actually become liquid in their own right. This photograph, or two photographs, just illustrate through a microsection the combination of the low temperature material into the sack alloy, and comes from one of the books that I illustrated earlier. So it gives you a feel for what's actually happening at a metallurgy level during the soldering process. Now, talking about the different sort of technologies, these are some examples of profiles used as part of the INME project, and it highlights the sack reflow baseline. As you see here, you see two examples of low temperature materials. So two variety of materials, not to be specific about them, but also it mentions about joint reinforcement and joint reinforcement paste. So you can see that the profile in blue is quite different from the tin bismuth and bismuth tin alloys, which we'll highlight that in a second. So in 2016, originally I was doing some more trials on low temperature materials, and like an engineer, I like to understand what the materials are, how they react. So we did reflow trials, solder balling trials, slump trials, all the sort of usual things that we would do to assess a product. And this is just an example. So the materials had improved quite a lot from the early days. And we built both boards with nickel gold and copper OSP. And the two examples I show here are on copper OSP substrates. you can see the joints forming perfectly. But always remember that with copper OSP and tin also, is you quite often see some evidence of the original pad surface still visible. That comes down to the volume of paste you put on to start off with. But they're a perfectly good and reliable interconnections that we show illustrated there. I mentioned the benefits of using this lower temperature material, as other engineers have highlighted, on intrusive reflow or pin in paste reflow. And these are just examples of the low temperature material being actually used on connectors, which actually can be obtained as a lower temperature version. And there is a benefit on the financial cost of the component, and fairly easy to achieve IPC standards with these materials, because it's the same basic volume of material that we're applying to the printed circuit board. When we move on to more recent trials in 2019, 2020, I was looking at materials both from Europe and also from China. And again, this is me looking at the material, its reflow characteristic, its slump characteristic. And again, pretty similar to any of the SAC materials you may be using today. So the actual materials being manufactured are quite stable and provide good printing characteristics as well as reflow characteristics. The only issue that I found is some of these joint reinforcement paste, which I'll explain in a moment, weren't quite as easy to print as traditional pastes. And these are just two examples of trials that I was doing. And here we're printing onto a glass substrate and then measuring and looking at the variability of the amount of paste that's actually applied during the printing process and some of the other characteristics of the material. But it's a good way of understanding what's actually going on in a process, and something that is useful also during paste evaluations. This is just a close-up of these materials. And fundamentally, the JRP materials are solder paste. But the interesting thing is they have an epoxy resin system within the non-metallic material, which makes up the solder paste. So when we actually take the material and reflow it, we're doing two things. We're making a mechanical, but also making an electrical interconnection. So if you look at a close-up of some of these reinforcement paste reflowing, as I've done previously with the other materials you've seen, then if we go to close-up, you not only see the reflow characteristic, but you also start to see the reaction of the materials, which will actually provide what we want, which is the retention force. So this microsection was taken again as an image from the book that I referred to, and it's not as clear, but on the image that you can see the cured resin at the side. Now I've added in a couple of lines here, yellow lines, just to highlight it. So basically what we're doing is we're soldering to the board, and then we're using epoxy technology to hold the joint to the board. So what this does is improve and overcome some of the disadvantages of the material not being as ductile as other solders. It potentially can be used to overcome mismatch expansion, but probably more likely is the benefit is overcoming the issues associated with mechanical handling, which is all down to ductility and ductility failures that we mentioned previously. Now, solderability and wettability is something we still need to understand with these low materials. I don't really think there's too many problems, but I always like to highlight things that people forget about. And if you take a solder paste and you change it and modify the type of fluxing system and temperature that it actually activates to start the soldering process off, what are the consequences? Well, consequences can be wettability and solderability of components and PCBs. So I've done a whole series of trials on different surface finishes with wetting indicators that you see on the video on the right-hand side, and reflow trials on all the quite common surface mount joints, just to see the wettability and solderability and how they change with these materials. We've seen it work successfully with area array packages. And many of these video clips that I've shown here on this presentation were actually included in a presentation I did at Apex. And you can get a fuller version of that presentation if you go to the Apex IPC website, if you're interested. Jumping on to rework and repair, I'm trying to cover a number of topics during this presentation. And what you see here is a speeded up version of an assembly trial I was doing with standard area array packages, with sack balls, but with low temperature materials. The low temperature materials are forming the joint, so I'm actually reworking these or doing a simulation of rework on these packages. So we've already reworked the board and then we're going back and putting the parts back. And again, you can see, if you look closely at the image, you can see that dividing line, what some people refer to as a waistline. The solder, that's the liquid stuff, and the ball, that's the solid stuff, but the two are making reliable interconnections between them. Now, on to a little bit of reliability. Because of lockdown, I haven't been able to do much work in this area practically on SMT and area array, but I've been doing some stuff on through-hole. And these are just some examples after multiple thermal cycles at -55, 125 on one of the tin bismuth alloys, and it's a through-hole joint. Through-hole joints very rarely ever fail in the real world of manufacture and in the field, I would hasten to say. But you will see changes. And I was able to see changes in the joints after temperature cycling, which did show some cracking. And you can see in these microsections, the first and second from the left to the middle of cracking. And also something that I quite often see on lead-free boards is pad lifting. Now, again, none of these would be considered a reliability issue, and I haven't seen them ever to be a reliability issue. But you may well see this type of issue when you start to do some environmental testing. But it's more likely you're going to see it in mechanical testing rather than just temperature cycling. We can also use X-ray, and in this example, I took those sample boards and we X-rayed them. And if you look around the barrel of the hole, that's the large black area on this X-ray image, you can actually see some evidence of cracking around the barrel and between the barrel and the pad. So again, the techniques we have on our shop floor today will allow us to still analyze and look at joints with the tin bismuth materials, which is fairly well understood. But sometimes when you use something different, people wonder whether or not it's going to be an issue or not. We also did some work on QFN, LGA packages. And again, because the packages are changing, improvements to the design to improve reliability, that's good for the automotive industry. But for other types of industries, perhaps not as demanding as that, the low temperature materials may well be used. But we can see with temperature cycling that we can introduce failures. And these are examples of some failures that we saw in our QFN work. And you can see these microsections and the ruptures taking place between normally the termination and the bulk of the solder rather than anywhere else in the structure. But that's just some nice examples. On to my final sort of subject of today, I wanted to mention about robotic soldering as something that I've been playing around with for the last 4 or 5 years, and it's something that I have a lot of interest in. Again, you can get the materials, they are available to be used, but the big problem is cord wires. There's only 2 suppliers within the industry that I'm aware of that provide cord wires. If you want to use preform materials, again, they're available in a wider range of materials for traditional soldering or other specialist applications. In 2015, I did a survey, and I do these quite often when I'm doing large webinars for groups on robotics. And this is basically what engineers, there were about 100 engineers, said at that time, that 82% weren't using robotic soldering, but 10% were using iron, and 4% were using laser. But that has changed in 2020 in October when I last did this. So 29% were using iron, 7% laser. So there's a slight increase, but obviously a decrease in those companies not using the technology. So there's a lot of interest in the use of robotics and robotic soldering. And Matt alluded to that in his presentation. And so much so, because I'm all about defects or solving defect problems, I put together a series of videos. So if you're interested, if you're using robotic soldering, there's a series of videos you can watch. They're free. They're on YouTube about some of the more common process issues with the use of robotic soldering. The fundamentals of soldering don't really change. So when you look at iron soldering, the steps are pretty much mimic of what you do with a soldering iron in the normal manufacturing environment, although it's automated. With laser soldering, it's slightly different in that we have solder wire that we feed to the joint, but we use the laser to preheat the board, to preheat the solder as it's coming to the joint, and then reflow the solder as we add solder volume to fill the plated through hole. But never forget nitrogen. That also can be a real benefit in the process and also speed up the process. But perhaps I'll talk about that on another day. So just as an example, these are demonstration boards that I put together as part of my NPL project. And we looked at the soldering performance, both on contact soldering, but also on laser soldering. As I said, contact soldering has become more popular possibly than laser because of more systems being available, but the speed of operation of laser is much faster than contact. So again, you've got to look at what's right for your particular application. And probably the biggest issue I'll address and speak about now is during the soldering process, solder ball formation. So when we feed solder into the robotic system, whether it be laser or whether it be contact, we use a wheel which indents the wire. And you can see in examples of indented wire at the bottom of this particular slide. And that's significant for two reasons. One, it feeds the wire, but more importantly, it reduces the pressure that builds up within the wire during the soldering operation. If you look at these examples here, I've got two at the top of the screen and I've got two X-rays at the bottom of the screen. And you can actually see where I'm pointing out the indents caused by the drive wheel and also the core where the flux is in the wire. And one little experiment that I conducted just to demonstrate this, here's some solder wire sitting on a flat sheet. I'm heating up the wire. And if you watch very carefully, you can see the flux come out of the core because of the indents, and that energy is escaping when there's not too much pressure. If it escapes too quickly, that's when we actually generate solder balls. So an example here from Seiko, that indexing wheel, but if you look very carefully, you can actually see the flux coming out of the wire just before it contacts the solder head. And that's one of the simple ways of overcoming the problem. And as I said, we looked at that during the work we did on our MPL report on high temperature and soldering with robotic systems. A couple of other things that can be beneficial using IR technology. And using IR measurement technology, simple systems that you can see here, it's good to benefit and see what temperatures are actually being achieved on a printed circuit board with non-contact during a robotic soldering operation. But also looking at the feed rate of nitrogen, the temperature of nitrogen coming into the process, and how that can improve and speed up the process is quite a good quality control tool to look at if you're looking at the use of robotic soldering in your process. So finally, just to summarize, if you'd like a copy of the presentation, a copy of the MPL report, or the free charts that I mentioned, just drop me an email and I'll be more than happy to send those on to you. And hopefully there'll be some questions, but I'd just like to mention that I run webinars every month throughout the year. And again, if this is something that's interesting to you, you can obviously visit the website and find out about the topics that I present. So any questions of anything that we've talked about during the session? Hopefully I may be able to pick up on any of them. And one of the things I must say, please type them in English. My foreign language skills leaves a lot to be desired. Leaves a lot to be desired. So I don't see anything in the question, open questions at the moment, but I'm sure my beautiful moderator assistant will be able to tell me yes or no.
Bob, thank you very much for your spectacular presentation. Now we see the main benefits of robotic soldering and also the low temperature assembly. And according to our agenda, speaker is still waiting. And you know, the low operating temperature of the audience will increase shortly. So is it also acceptable for you to stay with us for a while to answer your questions? Is it possible?
Yeah, more than happy. I'll sit quietly in the corner and answer any questions that I possibly can.
Okay, thank you very much for your participation.